The action potential arrives and depolarizes the axon terminal.
The depolarization of the axon terminal triggers the opening of the voltage-gated calcium channels, and calcium ions enter into the cell. After a brief delay, the entering of the calcium ions triggers the exocytosis of these orange circles here, the synaptic vesicles, which effectively dump the ACH molecules into the cell. For future reference, the pink bead is acetate and the blue bead is choline. Together they form ACH. They are dumped into the cell by the synaptic vesicles. Pretty quickly after they're entering, the calcium ions are removed from the cell, the channels close, and the ACH release is stopped.
The ACH that's released into the synaptic cleft binds to the sodium channels, which causes them to open and make sodium go into the postsynaptic membrane. If enough sodium goes into the membrane, it can start another action potential.
The ACH that did not bind to the receptor gets broken down by ACHE, which is already present in the synaptic cleft. And that process can take like 20 milliseconds.
So after the ACHE breaks down the ACH molecules, the A acetate cannot be recycled by the axon terminal, and instead diffuses across the postsynaptic membrane away from the site of the binding. The choline, in contrast, can be reabsorbed and is taken back into the axon terminal, where it works with CoA, acetyl-CoA, in the mitochondrion to form new ACH molecules, which are now ready to go and be released as neurotransmitters. The process as a whole takes about 0.2 to 0.5 milliseconds for the axon terminal to arrive and its effect on the postsynaptic membrane, which then is about how long it takes for it to be ready to fire again.